Hello everyone, this is Dennis, and you're on the Electro channel. Today I'll be reviewing this compact, multifunctional DC tester. It takes all the necessary measurements, such as voltage, current, power, temperature, and much more. This device also has a wide supply voltage range from 8 to 120 volts. It measures voltage from 0 to 200. The maximum current it can handle is 10 amps. It can be integrated into various devices, such as power supplies, whether factory-made or homemade, or chargers. It has a meter that records how much current has entered the battery, and after charging, you can calculate the battery's capacity. Now I'll show you how to connect it, tell you about its advantages, show you how to use it, and conduct tests. The tester looks like this. A small black plastic box measuring 85 millimeters by 44 millimeters. It's 21 millimeters thick. The front panel has just one button labeled Menu. The panel is made of very thin plastic, which bends easily under finger pressure. To prevent the tester from dangling after installation in a device, there are latches at the top and bottom. On the back panel, there's a sticker with a connection diagram for dual power supplies. To the left of this sticker are two connectors. 3 thin wires are inserted into the lower left connector. These are for powering the tester and measuring voltage. And 2 thick power leads for measuring current are inserted into the top connector. There's another small connector at the bottom for connecting a temperature sensor. The tester's body consists of 2 halves, which are held together with 4 screws. I removed the back panel and immediately noticed the large circuit board taking up the entire case. By the way, there's a protective film on the glass that prevents scratches. You can remove it if you want to reveal a shiny glass. On the left are the labels for the connected wires. In the middle is a 45 by 25 millimeters color LCD display, and on the right is a single button. There are many electronic components on the back. Some of them are occupied by the H6203 step-down converter. This is what enables us to achieve such a wide supply voltage range, from 8 to 120 volts. This converter's output always maintains a constant voltage of 5 volts with a maximum current of 1 amp. Its circuit includes a 47 microhenry inductor and 2 capacitors, 470 microfarad, 10 volts, and 10 microfarad, 160 volts. The KWS-1622 microchip appears to be a display driver. The MS51FB9AE is an 8-bit microcontroller with both memory and RAM. It contains the tester firmware. To the right of it is another small microchip labeled A63A. This codename hides the LM321 operational amplifier. Further to the right is a large 1-watt resistor labeled R005. Its resistance is 0.005 ohms. In this tester, it also acts as a shunt. When current flows through it, a voltage drop occurs, and the tester measures it, converting the reading on the screen into amperes. There are also several diodes on the board. One small one labeled WH is a 12-volt Zener diode, and three larger diodes labeled SS3 150. These are 150-volt 3-amp Schottky diodes. There are also three controls on the board. Two of them are potentiometers. One regulates voltage, and the other regulates current. They should be used if the tester's readings are not satisfactory. They allow you to adjust the voltage and current more precisely. Above them is the reset button. You can use it to reset the ammeter readings, but you should only press it when the ammeter is idling, meaning without a connected load, and shows any current. If the ammeter shows 0 without a load, as expected, then you don't need to touch the button. Near the connector where the temperature sensor is inserted, there's the inscription NTC 10K 3950. This means that a 10 kilo-ohm negative temperature coefficient thermistor is inserted there, and its marking is 3950. The temperature sensor included with the tester looks like this. Its cable is not very long, about 40 centimeters. At room temperature, the temperature sensor's resistance is 9 kilo-ohms. If I touch it, the temperature begins to rise, and its resistance drops. This confirms that the temperature sensor is not a thermocouple, as many people call it, but a thermistor. The screen has 6 sections with different parameters: measured voltage, power, temperature, measured current, and time. The last line displays the ampere-hour and watt-hour counters. Pressing the menu button switches between these parameters. The ampere-hour counter is very convenient when charging or discharging batteries. You can see how much current is being supplied to the battery, and therefore calculate its capacity. The temperature sensor works perfectly. When I touch it, the temperature begins to rise. If you remove the temperature sensor, the temperature section will be empty. The tester comes in a small box and has instructions in both Chinese and English. It contains a table with the specifications of all models of this tester. My device is in the first column. Model: KWS DC200-10A. The voltage the device can operate on ranges from 8 to 120 volts. The voltage of the power supply under test ranges from 0 to 200 volts. The maximum current without using a remote shunt is 10 amps. The maximum measurement power is 1200 watts. This is, of course, a bit of a misprint, as 1200 watts apparently refers to power from a single power source. This is at a voltage of 120 volts and a current of 10 amps. If you use two separate power supplies, one for the load and one for the tester, then at 200 volts and 10 amps, the power transmitted through the tester will be 2000 watts. Next are the parameters of the two ampere-hour and watt-hour meters. The maximum timer duration is 200 hours. Temperature measurement ranges from -9 to +99 degrees. The instructions also show two connection diagrams, one with two power supplies and the other with one. First, let's look at a circuit with two independent power sources. Here, two power supplies are required. One low power supply powers the tester, and the second high power supply powers the load. The low power supply is connected to the two thin tester leads, red and black. It should have a voltage between 8 and 120 volts. The positive terminal of the high power supply is connected to one terminal of the load, and the second terminal of the load is connected to the thick red lead of the tester. The thick black lead of the tester is connected to the negative terminal of the high power supply. This way, current will flow from the positive terminal of the high power supply through the load. It will then pass through the tester and exit to the negative terminal of the power supply. The thin yellow lead coming out of the tester measures the voltage. It must be connected to the positive terminal of a powerful power supply. In the more powerful 50 and 100 amp versions of this tester, the only difference in connection is that the remote shunt is connected to the black and red wires. These versions do not have the SMD shunt built into the tester body, so current will only flow through the remote shunt. This circuit is convenient because the voltage range can be varied from 0 to 200 volts, but the downside is that two power supplies must be used. Now let's move on to the connection diagram with a single power supply. This is much simpler. The power supply must be between 8 and 120 volts. If the voltage is less than 8 volts, the tester will not turn on. You can't raise the voltage above 120 volts, as this voltage will flow not only to the load, but also to the tester. Also note that although this photo is taken from the documentation included with the tester, it still contains an error. It states that the connected power supply must have a voltage range of 0 to 200 volts. This is incorrect. In this wiring diagram, the thin red wire coming from the tester must be connected to the positive terminal of the power supply. The yellow signal wire, which measures the voltage, is also connected to the positive terminal. The thin black wire is not connected anywhere. It will hang in the air. Otherwise, the circuit is exactly the same as with two power supplies. This circuit is convenient because it uses only one power supply. But a major drawback is that the voltage range used is only 8 to 120 volts. I'll show you how to connect a tester with a single power supply. The red thin wire connects to the positive terminal of the power supply. The black thick wire connects to the negative terminal of the power supply. After this, the device turns on, but doesn't measure voltage yet. To fix this, connect the yellow wire to the positive terminal of the power supply. Now you can see that the input voltage is 12.5 volts. The black thin wire is also negative. And if you connect it to the thick black wire, nothing will happen. However, connecting it when using a single power supply is not recommended. For the load, I'll connect a small 12-volt light bulb. I attach one end to the thick red wire and the other to the positive terminal of the power supply. The light bulb lights up immediately, and current flows through the tester. The device immediately records the current flowing and calculates the bulb's wattage. With two power supplies, the connection will be as follows. The weak power supply is connected to the thin black wire and the thin red wire. The negative terminal of the powerful power supply is connected to the thick black power wire. The positive terminal of the powerful power supply is connected to the yellow test lead. Note that the tester immediately records the incoming voltage after this. The load is connected to the thick red power wire at one end, and to the positive terminal of the powerful power supply at the other. With two independent power supplies, the voltage can be adjusted to a minimum. Thanks to the separate power supply, the tester won't shut down. I can't comment on the measurement accuracy of this tester, as I don't have a super precise reference device to compare it to. But if anyone's interested, here's a comparison with the ZK5KX converter. Both devices show almost the same voltage, and the current in hundredths differs slightly. At 36 volts, both show the same. Next, I'll show how things work with heating when measuring maximum current. I taped the temperature sensor to the shunt to record its heating. I apply a load and gradually increase the current. I've sped up the video 3 times to show how quickly the resistor heats up. I'll start by applying about 9 amps. After about 10 minutes of operation, the shunt's heated up to 49 degrees. The circuit board on the back of the shunt is also hot. The wires are also hot. I'll try increasing the current and see what happens. Although the tester is advertised as a 10 ampere tester, it can actually read more. In this case, it's almost 12 amps. I won't increase the current any further, as the shunt isn't designed for that much power. If the tester's power is disconnected, the time, watt-hour, and amp-hour counters are not reset. After powering on, everything is saved. To reset the readings, hold down the menu button for 3 seconds. After this, all counters are reset. I notice that this meter has a slight delay in updating its readings, but this will only be noticeable under a dynamic load. For example, when measuring the current consumption of an audio amplifier. If you connect a light bulb or some other resistive load, the effect of the delay in readings will be almost unnoticeable. Now I'll connect the load. Watch the screen and the light bulb carefully. Power is 0.93 watts and current is 80 milliamps. When I disconnect the light bulb, the meter updates these readings very slowly. There is essentially no load, but the meter still displays a small portion of it. Look at this again. The slow update rate is only observed for watts and amps. This doesn't happen for voltage. When the voltage increases or decreases, it updates quickly, just like on a laboratory power supply. I'll leave a link to this tester in the description. As always, like this video, subscribe to my channel if you haven't already. Click the bell to stay up to date with new videos. And leave comments and ask questions if anything is unclear. That's all for today. Bye, everyone.